Yes, the ground wire is required to be connected to the box, even with grounded conduit. The conduit's grounding is not sufficiently reliable. The ground wire serves as a backup for fault current flow and protects the receptacle from damage during a ground fault. Section 215.118 mandates grounding of all non-current carrying metal parts, raceways, and enclosures, including metal boxes. Section 250.146 specifies that the equipment grounding conductor must connect to the equipment grounding terminal or bonding jumper. Section 250.146b states that if the enclosure has a grounding terminal, the equipment grounding conductor must connect to it. Section 250.146d dictates that when the grounding path is through metal raceway, the equipment grounding conductor terminates where the raceway connects to the grounding electrode system. The fine print note to Section 250.146 allows the equipment grounding conductor to run with circuit conductors when raceways are used for equipment grounding, as in your scenario. While the conduit offers a grounded path, its reliability is questionable. The ground wire acts as a backup for fault current and protects the receptacle, making the connection mandatory. In essence, the National Electrical Code prioritizes a redundant grounding system to enhance safety and minimize risks associated with ground faults. This redundancy ensures that even if the primary grounding path, such as the conduit, fails or becomes compromised, there's still an alternative path for fault current to safely return to the source. This is vital for quickly tripping the circuit breaker or fuse, thereby preventing electrical shock hazards and reducing the potential for fire. Firstly, consider the mechanical integrity of the conduit system. Over time, connections can loosen due to vibration, corrosion, or physical damage. These loose connections can significantly increase the impedance of the grounding path, hindering its ability to effectively carry fault current. A supplementary ground wire provides a more direct and reliable low-impedance path, minimizing the impact of any degradation in the conduit system's grounding integrity. Secondly, the ground wire offers a lower impedance path compared to the conduit. Electrical impedance is the total opposition a circuit presents to alternating current, and it includes both resistance and reactance. A lower impedance path allows for a greater fault current to flow, which in turn helps to trip the overcurrent protection device, circuit breaker, or fuse faster. This faster response time is crucial in limiting the duration of a fault and minimizing potential damage. Thirdly, the presence of a ground wire mitigates the risk of voltage gradients. During a ground fault, current flows through the grounding system back to the source. If the grounding system has high impedance, the voltage potential can rise significantly at various points along the path. This can create a dangerous situation where different metal parts of the electrical system have different voltage potentials relative to ground, increasing the risk of electric shock if a person comes into contact with two such parts simultaneously. A ground wire helps to equalize the voltage potential throughout the grounding system, reducing this risk. Fourthly, the ground wire provides enhanced protection for sensitive electronic equipment. Modern receptacles often serve devices containing delicate electronic components that are susceptible to damage from voltage surges or transient currents. A robust grounding system, including a dedicated ground wire, helps to divert these surges away from the equipment, protecting it from damage and ensuring its reliable operation. Fifthly, the code requirements are not arbitrary. They are based on years of experience and analysis of electrical incidents. The NEC is continuously updated to reflect the latest knowledge and best practices in electrical safety. The requirements for grounding and bonding are among the most critical aspects of the code, and they are designed to protect people and property from the hazards of electricity. Ignoring these requirements can have serious consequences. Sixthly, consider the specific requirements outlined in the NEC sections mentioned earlier. Section 215.118 emphasizes the grounding of all non-current carrying metal parts. This broad requirement underscores the importance of creating a comprehensive grounding system that encompasses all metallic components that could potentially become energized during a fault. Sections 250.146(8)b and d provide detailed instructions on how to properly connect the equipment grounding conductor to ensure effective grounding and bonding. The fine print note to section 250.146 further clarifies that the equipment grounding conductor should run with the circuit conductors, reinforcing the concept of a dedicated grounding path. Seventhly, it's important to understand the difference between grounding and bonding. Grounding refers to connecting the electrical system to the earth, which provides a reference point for voltage and helps to stabilize the system. Bonding, on the other hand, refers to connecting together all metal parts of the electrical system to create a low impedance path for fault current. Both grounding and bonding are essential for electrical safety. Eighthly, when installing a receptacle in a metal box, it's crucial to ensure that the receptacle is properly grounded. This typically involves connecting the equipment grounding conductor to the grounding terminal in the receptacle. If the metal box is also properly grounded, this creates a redundant grounding path that further enhances safety. Ninthly, it is essential to use the correct size of ground wire for the circuit. The size of the ground wire is determined by the size of the circuit conductors, and it must be able to safely carry the maximum fault current that could occur. Using an undersized ground wire can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. Tenthly, regular inspection and maintenance of the electrical system are crucial for ensuring its continued safety and reliability. This includes checking the tightness of connections, inspecting for signs of corrosion or damage, and testing the effectiveness of the grounding system. Any problems that are identified should be promptly addressed by a qualified electrician. The presence of the ground wire alongside the conduit provides several critical benefits for electrical safety. It acts as a reliable backup, lowers impedance, mitigates voltage gradients, protects sensitive equipment, and ensures compliance with code requirements. Therefore, connecting the ground wire to the metal box is not only a code requirement but also a best practice for ensuring the safety and reliability of the electrical system. The ground wire is installed in addition to the conduit because the conduit connections could come loose over time due to vibration, physical damage, or corrosion. This could lead to a high impedance ground, which would not trip the breaker quickly in the event of a fault. The ground wire provides a low impedance path for fault current to flow back to the source, which will trip the breaker quickly and safely. Also, without the ground wire, a fault could energize the metal box, creating a shock hazard. The ground wire ensures that the metal box is always at ground potential, which eliminates this hazard. In addition to the safety benefits, the ground wire can also improve the performance of electronic equipment. Electronic equipment is often sensitive to voltage fluctuations and noise. A good grounding system can help to reduce voltage fluctuations and noise, which can improve the performance and reliability of electronic equipment. Therefore, even though the conduit is grounded, it is still important to install a ground wire to the metal box. The ground wire provides a backup ground path, reduces the risk of shock, and improves the performance of electronic equipment. Always consult the latest edition of the NEC for specific requirements and guidance on grounding and bonding. Adhering to these requirements is essential for ensuring the safety and reliability of electrical systems. Also, consider the environment where the electrical system is installed. In corrosive environments such as those near the ocean or in industrial settings, the conduit and its connections are more likely to corrode over time. This corrosion can significantly degrade the grounding path, making the ground wire even more critical. In these environments, it's important to use corrosion-resistant materials for the conduit and fittings, and to regularly inspect and maintain the grounding system. Another factor to consider is the type of equipment being powered by the circuit. If the circuit is powering sensitive electronic equipment, such as computers or medical devices, a dedicated equipment grounding conductor is even more important. These types of equipment are more susceptible to damage from voltage surges and noise, and a robust grounding system can help to protect them. Moreover, the use of isolated ground receptacles may be considered in situations where sensitive electronic equipment is particularly susceptible to noise. Isolated ground receptacles have a separate grounding path that is isolated from the building's normal grounding system, which can further reduce noise and improve performance. However, it is important to note that isolated ground receptacles must be installed in accordance with the NEC and they should only be used in specific situations where they are necessary. In addition to the above, it's crucial to understand the role of bonding jumpers in the grounding system. Bonding jumpers are used to connect together different metal parts of the electrical system, such as metal boxes, enclosures, and raceways. These jumpers ensure that all metal parts are at the same electrical potential, which reduces the risk of electric shock. Bonding jumpers should be properly sized and installed in accordance with the NEC. Furthermore, surge protective devices (SPD) can play a significant role in protecting electrical equipment from voltage surges. SPD are designed to divert surge current away from sensitive equipment and back to the grounding system. SPD should be installed at the service entrance and at any other points in the electrical system where surges are likely to occur. It's also important to consider the impact of harmonics on the grounding system. Harmonics are distorted waveforms that can be generated by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause overheating of conductors and equipment, and they can also interfere with the operation of sensitive electronic equipment. A properly designed grounding system can help to mitigate the effects of harmonics. In summary, connecting the ground wire to the metal box is a fundamental requirement for electrical safety, and it provides several critical benefits. The ground wire acts as a reliable backup, lowers impedance, mitigates voltage gradients, protects sensitive equipment, and ensures compliance with code requirements. Always consult the latest edition of the NEC for specific requirements and guidance on grounding and bonding. Remember to carefully consider the environment, the type of equipment being powered, and the potential for voltage surges and harmonics when designing and installing the grounding system. A well-designed and properly installed grounding system is essential for protecting people and property from the hazards of electricity. The size of the equipment grounding conductor is generally determined by Table 250.122 in the National Electrical Code, and is based on the size of the overcurrent protection device circuit breaker or fuse protecting the circuit. For example, if you have a 20 amp circuit, Table 250.122 typically requires a 12 American wire gauge copper equipment grounding conductor. If you have a 30 amp circuit, a 10 American wire gauge copper conductor might be required. Always refer to the latest version of the NEC and consult with a qualified electrician to determine the appropriate size for your specific application. When connecting the equipment grounding conductor to the metal box, make sure to use an approved grounding connector or lug. The connector should be properly sized for the conductor and should provide a secure and reliable connection. Also, be sure to clean any paint or corrosion from the metal box before making the connection to ensure good electrical contact. If the metal box is already equipped with a grounding screw, you can simply connect the equipment grounding conductor to the screw. However, if the box does not have a grounding screw, you will need to install one. You can purchase grounding screws at most electrical supply stores. When installing a grounding screw, make sure to drill a hole in the box that is the correct size for the screw. Also, be sure to debur the hole after drilling to remove any sharp edges that could damage the conductor. Finally, always torque the grounding connections to the manufacturer's specifications. This will ensure a secure and reliable connection. Over-tightening the connections can damage the conductor or the connector, while under-tightening the connections can lead to a loose connection, which can cause overheating and electrical hazards. In addition to connecting the equipment grounding conductor to the metal box, it's also important to bond the metal box to the metal conduit. This can be done by using a bonding jumper. The bonding jumper should be sized according to Table 250.102 in the NEC, and it should be connected to both the metal box and the metal conduit using approved connectors. As mentioned earlier, regular inspection and maintenance of the electrical system are crucial for ensuring its continued safety and reliability. This includes checking the tightness of grounding connections, inspecting for signs of corrosion or damage, and testing the effectiveness of the grounding system. If any problems are identified, they should be promptly addressed by a qualified electrician. In addition to visual inspections, it's also a good idea to perform periodic testing of the grounding system. This can be done using a ground resistance tester. A ground resistance tester measures the resistance of the grounding system to earth. A low resistance reading indicates a good grounding system, while a high resistance reading indicates a problem with the grounding system. If the ground resistance reading is too high, you should consult with a qualified electrician to troubleshoot the problem. Common causes of high ground resistance include loose connections, corroded connections, and damaged grounding conductors. The NEC also addresses the use of listed or labeled equipment. When using electrical equipment, it's important to make sure that it is listed or labeled by a recognized testing laboratory, such as Underwriters Laboratories UL or Intertek ETL. Listed or labeled equipment has been tested and certified to meet certain safety standards. Using listed or labeled equipment helps to ensure that the electrical system is safe and reliable. The NEC also covers the requirements for working on electrical equipment. Only qualified persons should work on electrical equipment. A qualified person is someone who has the skills and knowledge necessary to safely work on electrical equipment. When working on electrical equipment, it's important to de-energize the circuit before starting work. This can be done by turning off the circuit breaker or removing the fuse that supplies power to the circuit. After de-energizing the circuit, it's important to test the circuit to make sure that it is actually de-energized. This can be done using a voltage tester. Also, always use appropriate personal protective equipment (PPE), such as safety glasses, gloves, and insulated tools when working on electrical equipment. The requirements of the NEC are quite detailed and complex, but they are all designed to protect people and property from the hazards of electricity. By following the requirements of the NEC, you can help to ensure that the electrical system is safe and reliable. Remember to consult with a qualified electrician if you have any questions or concerns about the electrical system. Also, always refer to the latest edition of the NEC for specific requirements and guidance on grounding and bonding.